Okay, I apologize in advance that this video may be a little lengthy. We're going to start with area, and we're going to try to cover basically the two objectives from section 7.7. And so what that includes is not just the area of the circle, as we know from our previous courses and previous units, but also the area of sectors, which is basically like a slice of the pizza or a slice of the pie, and segments, which would be a slice of the pizza, but only counting like the crust. Basically, what a segment in a circle is the whole sector minus the little triangle that is formed between the two radii, and then this segment right here that would connect like point Z to point M or point A to point B. That segment is called a chord, C-H-O-R-D, and so essentially what we do is we find the area of that sector first, which we're going to chat about. We subtract the area of that triangle, which we already know how to determine, and then that leaves us with the area of the segment. That's going to be our approach here in geometry class. So the first thing that we need to remember is that the area of a circle is pi times the radius squared. It's important that you understand that it is the radius that is squared, and then you multiply by pi. I know that the order in which it's written is maybe not conducive to that understanding. It's not pi times the radius and then square that product. It's pi times the radius squared. So follow that order of operations, use the exponent first, and then multiply that squared radius by pi. All right. When we are finding the area of the or a sector of a circle, the area of what is that the area of the slice of the pie or the slice of the pizza, essentially what we understand is very similar to what we did in section 7.6, where we were finding the length of the arc was a fraction of the whole circumference. Likewise, the area of this sector is a fraction of the whole area of the pie or of the pizza. And so essentially what we're going to do with these, I'm going to erase this in just a sec, but let's try to do this first one up here, is we are going to find the area of this sector of the circle is found by taking the measure of the arc, all right, which in this case is arc ZM, the measure of arc ZM divided by 360 multiplied by pi times the radius squared. All right, and in this case, the only thing that changes from item to item is going to be the measure of the arc and the length of the radius that we are squaring. Those are the only variables. The 360 stays the same, the pi stays the same, the squaring stays the same. And so we have 72 divided by 360 times pi times the radius in this case is 20. The radius in this case is 20, and we will square it. And so if we are using our calculators to do that multiplication, we essentially are going to multiply 72 over 360. You can't see that very well. 72 divided by 360 times 20 squared. All right? And then that will give us the total area of that sector, which in this case is 80 pi, and again our units are squared centimeters, centimeter squared. All right? And so essentially what we're doing is we're taking the measure of the arc, or the measure of the central angle, divided by 360 times the area. A fraction of the area of the circle is going to be this shaded sector. When we're talking about a segment of a circle, that essentially again is a sector where we've subtracted out the triangle. It's essentially part of the circle that is contained between this chord that connects AB, segment AB, and the arc AB. And a very straightforward approach for calculating that area, and again, working in terms of pi, finding the exact value. This might be a little bit difficult algebraically, but we are going to find the area of the sector like we did in the first example, and then subtract out the area of the triangle. There's a couple things that you need to know before we begin doing that. First of all, I hope that this graphic makes sense. Again, you can reference the PowerPoint notes, or you can reference your textbook on that for more explanation if you care. But the thing that you need to understand is that these triangles that we're dealing with here are bounded by radii, and so we know that these triangles are isosceles. And so we should have some sort of approach or some logical thinking that we can use to find the area of those isosceles triangles. We can use trigonometry, we can use special right triangles as we will here, or we can just use base and height as is appropriate. So I'm going to have to erase this part of the picture of the board so that I have space in which to do my work. So bear with me for just that moment. And essentially what we're going to do is we're going to find the area of this sector. All right, we're going to find the area of the segment is going to equal the area of the sector minus the area of the triangle. So in this case, the area is going to be the fraction of pi times the radius squared. All right, pi times, and I'm going to put in these, this is the radius, this is the measure of the central angle or of the arc, and then we're going to subtract, 1/2 of the base of the triangle times the height of the triangle. All right, so essentially that's what we're doing. There is obviously this background knowledge that we have to apply of 1/2 times base times height. All right, and we're going to substitute our values for the measure of that central angle or the measure of that arc and the value for the radius. So for this example right here, we are going to say that the area is 90 over 360 times pi times the radius of 10 inches squared, but then we're going to subtract 1/2 of the base times height. This is a right triangle, so the base and the height in this isosceles right triangle all are the same. And so essentially what we have here is 1/4 of 100 pi. 1/4 of 100 is 25. And then we are subtracting 1/2 of 100. So we get that the area in this second example here is 25 pi minus 50 square inches. All right, so we're going to have this many square inches. Now I know that looks a little bit complicated, all right? Part of the reason is these are not like terms, I can't combine them. We multiply this, we can find the area of that sector, we can find the area of that triangle by multiplying those. When we go to subtract, we can't actually subtract them to write it in a more simplified form than this. We can obviously approximate that, and I can confirm with you that 25 pi is greater than 50. 25 pi is greater than 50, it's 78.5. So if I were to subtract 50 from 25 pi, oops, let me do that, 25 pi, oops, wrong buttons, 25 pi minus 50, it'll give me a decimal approximation. All right, sorry if you can't see that, there we go, 28.5. And so we want to make sure that we can, that we are okay with doing that multiplication here and the multiplication there, and then stop. Sometimes we get carried away and we want to combine these terms. Well, 25 minus 50 would be negative, right? Negative pi's, and we don't have negative pi's happening here. We're just talking about the crust here. And so it's part of that sector, but it is not going to be greater than that sector, all right? For the second piece right here, this is a little bit more complicated of an example, and sorry for the sloppiness there. You can see that example more clearly in the PowerPoint notes, but it's going to be the same situation, except that finding the area of that triangle is going to be a bit more difficult. All right, so again, this is an isosceles triangle, and I want to talk about that triangle first. With this isosceles triangle that has 24 feet, 24 feet, and then a 120-degree angle here in the at the center of the circle, the way that we're going to find that area is by drawing in the altitude. All right, drawing in the altitude. And when we do draw in that altitude, something special happens. All right, we're going to go back to Chapter 7, Section 3, Special Right Triangles. We cut this 120-degree angle into 60 and 60, which means that this perpendicular distance here from this line segment to this line segment, that perpendicular distance from this line segment to this center of the circle, the vertex here, is going to be half of 24. Which means that this piece is going to be that short leg times the square root of 3, which means that this is also that short leg times the square root of 3. And when we add them together, we get 24 times the square root of 3, and this was in feet. These are in feet. All right, this is 12 feet. If you didn't follow that, go back to Chapter 7, Section 3, rewind the video, whatever you need to do. But here we have an isosceles triangle with 120 degrees. I cut that in half to do base times height times 1/2, or 1/2 times the base times the height. So So I can find that area. I use 30, 60, 90 rules to find out that this is 12 and that this is 12 square roots of 3. There are two of them together, which makes 24 square roots of 3. The area of our segment, in this case, is going to be the area of this sector, which again is 120 degrees out of 360 degrees, times pi times our radius squared, minus 1/2 times the base, 24 square roots of 3, times the height of 12 feet. And so when we're finding the area of this segment, we're taking 1/3 of 24 squared, 1/3 of 576, gives me 192 pi. And then I'm subtracting half of 24 square roots of 3 times 12. So 12 square roots of 3 times 12 is going to be 144 square roots of 3, and this is in square feet. Now I know that working in lowest terms, simplest radical form, in terms of pi, trying to combine them, it looks really, really difficult. It looks really intense. If you saw that this was the answer and you didn't think through any of the work, you'd say, hey, that looks really complicated. My answer up here, I get that, Mr. Hibbett. My answer down here, what the heck is happening? What I want for you to recognize and see is this part is fine. You can do this part. This part should be fine. You should be able to do this part from Chapter 7. Again, if you need to review that content, go back to Chapter 7 notes, go look at your Chapter 7 in your textbook. But then when we try to combine these, this is in terms of pi, this is in simplest radical form. They are not like terms and therefore they cannot be combined. Here's how you find the area of the sector of a circle. Here's how you find the area of a segment of a circle. And obviously 2 levels of difficulty as we work through those. But rooted in this opportunity to work in terms of pi and find the area of circles.